Good morning, everyone. This is Sundar Atre, and we will be going over lecture 3 on the use of property charts for guiding material selection. This is part of the series of lectures for the design to manufacture digital tools. On this slide, you will see, for example, a plot of strength versus maximum service temperature. What types of information are buried in this type of a plot? How are they derived? How do we use that in material selection? This is the story of today's lecture. In the previous class, we have introduced the concept of materials index. Have you had a chance to review that? To consider what is a material index and why is it useful, let's take a look at component performance. Normally, we would have a set of properties that define its selection in a design. So, for instance, tensile strength. Alternatively, you would need a combination such as stiffness to density ratio or E by rho factor. Either the single property or this type of a ratio, which represents one type of a combination of properties, is considered to be a materials index for the purpose of design. So we go from single component indices to combinations as listed over here that depend upon shape, depend on other factors as well. The advantage of being able to work with material indices in this manner is that once we apply constraints, we can begin to create protocols for optimization of the material selection by choosing the biggest or the smallest index that is formulated for that particular design. The optimization techniques will be covered during module 2. Let us in this class look at how these properties are plotted against each other and how the derivation of materials indices and representing them in a chart across the board for various materials helps in learning some new things about materials and where they would be useful. Take a look at this plot again that we considered of the modulus in gigapascals versus density. What are some things that you notice? One thing you notice is the lightest materials tend to be in the bottom left corner and consist of foams. The heaviest materials tend to be metal alloys, and many of them are refractory metals. Tungsten, rhenium are kinds of examples in this region. The term heavy as lead, yeah, it is heavy, but there are things that are lead that are heavier than lead even. There are even ceramics that are heavier than lead. Gives you an idea. On the other hand, when you consider modulus, ceramics end up being some of the highest, showing some of the highest properties, as shown by this yellow region over here. The other thing to consider is this combination. Materials tend to group or cluster around each other, material classes, right? So metals technically tend to be heavier and tend to have a higher modulus. Foams tend to be lighter and have a low modulus. Polymers, there's fall somewhere in between. Even within polymers, let's take a look at some natural materials. For example, wood. You would see that the modulus parallel to the grain has one class of properties in terms of modulus, whereas perpendicular to the grain, you end up having a distinctly lower modulus. So what does that teach us, for instance, would be useful to know. Also, you could see that within foams, there are larger property variations as there's a distribution of foam porosity size distribution and volume fraction. While this particular chart strictly is for Young's modulus versus density, typically for most materials, including metals, ceramics, and glassy polymers and glasses, you can derive the shear modulus as well as the bulk modulus through these by multiplying these factors. Right? And so this can be this particular plot, which is for Young's modulus, can be used to estimate shear modulus and bulk modulus, which may not be explicitly given. For elastomers or rubbery polymers where the elongation is very high, this factor is altered for both the shear modulus and the bulk modulus, but by using that appropriate multiplication factor, you can estimate those properties of these property charts as well. Let's revisit a simplified version of this Young's modulus versus density. There is one more useful information that emerges out of that. It turns out that the speed of sound depends on both the modulus and the density, and here is a relationship. So the speed of sound varies as the square root of the ratio of modulus over density. So what does this mean? So if you have this E versus rho plot, we can now estimate the sound that propagates through a solid through the intercept in this plot. So if you take logarithms on both sides, after squaring, you will get the intercept to be 2 times the logarithm of velocity. And so in this E versus rho log plot, you will be able to estimate the velocity of sound. And so as you go to higher regions in this E versus rho plot and higher intercepts, you will be able to get larger values of sound propagating through this. Some things to consider in terms of what are the implications of this plot for either designing musical instruments or for using the propagation of sound for being able to evaluate defects or estimate material properties, such as the modulus. So for instance, ceramics over here give the highest propagation of sound, and so can be great for making chimes and musical instruments if so desired. Also, wood is used in a variety of musical instruments, flutes, string instruments, and so on. And when you remember that we had wood grain orientation affecting the propagation of sound, think about how that is taken into account when fabricating musical instruments out of wood. Okay, by implementing this relationship between the speed of sound and modulus and density, so material composition.